magnitude of vibration, and they will have the same frequency. Now we will talk about what is a sinusoidal transfer function. The sinusoidal transfer function, usually it's written like this, J, G omega. Is nothing, but it is the same transfer function, except you substitute S is equal to J omega. As simple as that. When you substitute S is equal to J omega, it will be sinusoidal transfer function. Then in this case, when the motion is sinusoidal, we have seen that the poles are located on the G axis. For the sinusoidal, when there is sinusoidal motion, there is real and the imaginary axis. The poles are located on the imaginary axis here. So we will substitute every S by J omega. If you substitute S by J omega, you will get J, G omega. And this is called the sinusoidal transfer function. Now, if we have the steady state, we derive the steady state equation by the sinusoidal input. We have a sinusoidal input of this form. P of t is equal to P sine omega t. The output will be x of t. This is in time domain, t domain. If you transfer this one to S domain, this will be x of S, and this will be P of S. So this is in Laplace domain also. So the input is P of S, the output is x of S. So if the input is like this, P of t is equal to P sine omega t, so we expect the output to be of this form. The magnitude of J G omega times the magnitude of the input sine omega t plus phi. Omega is known as same as the input. Same. Omega is the frequency of the input. So this and this are same, omega. But all we need to know is to calculate Jg omega, which is the magnitude of the transfer function. P is known, and we need to calculate phi also, which is the phase angle. So once we know J of S, the transfer function, we calculate Jg omega by just substitute S is equal to J omega. And then we take the magnitude of Jg omega, we multiply it by P, and all this Jg omega times P, this will be a constant, this will be a number. So it will be like capital X. So small x will be amplitude x times sine omega t plus phi. We will see now how to calculate J, G omega, and how to calculate phi. So this is all theory. You don't need it. So here we are. Here, this is what we have here. So the input, they will be like this one. The output will be in this form. X of t will be J, G omega times P is equal sine omega t plus phi. We can substitute this in this form, x, where x is equal to the pink one here. The pink will be Jg omega times P, and the phi is this angle, which is the phase angle. So this is what do we have now. X will be Jg omega times P. This is the amplitude of the output, amplitude of output, and this is the phase angle. So it turns out, just to know what will be Jg omega, and you are done. Once you know Jg omega, you will be able to calculate the phase angle, and you will be able to calculate the amplitude of the output. The annual amplitude of the output will be the amplitude of Jg omega times P. So here, this is the summary of all what we are doing here. This is the input, A sine omega t. The input has an amplitude of A, and it has a magnitude omega, frequency omega. The frequency of the input and the frequency of the output are same frequency. So now, the transfer function is Jg omega. The output will be capital X sine omega t plus phi. Capital X is simply the magnitude of Jg omega times P, or times A, which is the amplitude of the input, times A. This is A, amplitude of the input, So we'll call it input amplitude, which is A, A, and the phase angle is the phase of J, G omega. How to calculate this phase and the G is like this. Here, same thing, Shabab. This is A. I don't know, sometimes just copy and paste, or for new version, I did not update it. This is A, amplitude of the input. So going this way, we end up by having this. What will be the amplitude of the JG omega? It will be the amplitude of xj omega, output amplitude, over the input amplitude. The phase angle will be 10 minus 1, the imaginary part of JG omega, over the real part of JG omega. If you are working in, for example, in S-plane, usually when you have a number here, or a complex number S, which has a real part A and imaginary part B, the angle it makes, phi, it's always B over A. So here phi is equal to 10 minus 1. The imaginary part is B over A, always like this. So that's why we are saying imaginary of JG omega over the real part of JG omega. So the steady state response we are looking for will be of this form. The steady state will be X, will be capital X, sine omega t plus phi. Where this X, the amplitude of the output, will be like this. X will be the magnitude of JG omega multiplied by the amplitude of the input, P or A, whatever it is, amplitude of the input. So this is the input amplitude. Whether it is A or P, it doesn't matter. Input amplitude. And the phase angle JG omega is equal to phi. Phi is equal to the angle made by JG omega. I will show you one example here, a small example. We will be able to follow it. Find the steady state response. شباب هنا the steady state response. لأنه you remember we said the transient will die. So the transient will die and the solution will be exactly the steady state. So if the input is given by P sine omega t, the transfer function will be the output x of s divided by the input P of s, which is J of s. J of s is given, this is given to you, given T of s, as if 1 over Ts plus 1. Now, if we substitute s is equal to j omega, we will find jg omega, 1 over T j omega. Here, s will be equal to j omega. S equal j omega. We just substitute s is equal to j omega. So this is j omega. What will be the amplitude of this, the magnitude of this? It will be the magnitude of the numerator, which is 1, over the magnitude of this one is the real part square plus the imaginary part square. The real part is 1. The imaginary part is T omega. So we'll have T square plus omega square. So the amplitude or the magnitude of the transfer function will be 1 over square root of T square omega square plus 1. The phase angle will be simply the phase angle of this one, the numerator. So it will be the phase angle phi will be 10. And 1 has 0 imaginary number, so 10 0 over 1 minus 10 minus 1. This is 10 minus 1. 10 minus 1, the imaginary part over the real part. The imaginary part is T omega divided by the real part will be this one. 10 minus 1, 0 is 0. So this one will be equal to 0. So we end up by having phi will be minus 10 minus 1 T omega over 1 will be T omega. So in this case, we will write our steady state output, X steady state output, will be the magnitude, which is G omega. This one is the magnitude, times P, the amplitude of the input. Input has amplitude P, sine omega t minus phi. Phi هنا is given by this one. Minus 10 minus 1 omega t omega. Any question, Shabab?
Doctor, can you go back to output input? How did we get it?
This is the input, the amplitude, this is the input هنا, this is the input A sine omega t. The output will be X sine omega t plus phi. The output X هذا is A هنا, this is A, the amplitude of the input. This is A. So JG omega magnitude times the amplitude of the input, and phi is, so X sine omega t plus phi. This is the output. The input given, the output is this one. All you have to do is to find X, what is X and what is phi. X is magnitude of J omega, JG omega, times the amplitude of the input, and then the phase angle will be JG omega. Clear, Abdul Karim?
Yes, but can you go back to the example?
So now we have, this is our transfer function, Shabab. Our transfer function is this one. When we substitute from here, when we substitute S is equal to J omega, S is equal to J omega, we will find this one. This one, JG omega, can be written like this. JG omega can be written like this. Or, sorry, there is no square root. It can be just real part. This is the real part. This is real. Real equal to 1. The imaginary part, as you can see, is equal T omega. So the real part is 1, the imaginary part is T omega. You know, when we calculate the magnitude of any number, we have to square the real part, real square, plus the imaginary square under the square root. This is the magnitude. So this is what we are doing here. The magnitude here, 1 over the imaginary part square will give you T square omega square, plus the real part, which is 1 square under the square root. So this is the magnitude or amplitude. The phase angle, there is a rule like the log. It say phi will be 10 minus 1 numerator minus 10 minus 1 denominator equal 10 minus 1 numerator and the real part, yani the imaginary part is 0 over the real part, which is 1. 10 minus 1, the imaginary part is 0 over 1. Minus 10 minus 1, the imaginary part is T omega over the real part 1. Then we already explained that the phase angle will be the imaginary part over the real part. This one, if you split this 10 minus 1, 0 over 1 will be 0. So at the end of the day, you will find phi is equal to minus 10 minus 1 T omega. And this is the phase angle, which is the same thing. Magnitude is the same thing. Now, the x of t will be equal to JG omega, amplitude of JG omega 1 over T square omega square, this is the imaginary part, plus 1, all under the square root, or I will put it to the power 0.5, multiply by the amplitude of the input. Amplitude of the input is P here, is given to be P. This is the X, our X, capital X. And then sine omega t, phi, my phi is minus, this is phi, which is minus 10 minus 1 T omega. Is this clear, Dubis?
Yes, it's clear. Thank you.
Now, if we draw, Shabab, just drawing, so we wrote them like this one. If we draw the amplitude X as you can see, شوفوا شباب, when omega increases, the amplitude goes to zero. The amplitude goes to zero. This is for a force that is P is equal 10 Newton, 7 Newton, 5 Newton, 2 Newton, and so on. So for a T, which is 2 seconds, for a period of 2 seconds. So we have here the amplitude, as you can see, if you increase omega, the amplitude will be reduced. Here, what we are doing here, we are changing T, then T square omega square plus 1. We are changing T, but we are fixing omega. We are changing T and omega both. Here we were changing omega and P, but here we are fixing P is equal to 5 Newton, but we are changing at the same time T and then omega. So as you can see, when omega increases, in both cases, the amplitude will decrease, but the amplitude will go faster for smaller time, that is T. As you can see, T is equal to 10 seconds, that it will take longer time to reach zero. But if T is equal to 0.5 seconds, it's fast. It goes faster, and so on. So these are the amplitude versus omega, and amplitude versus omega at different P and different T. This is the phase angle, how the phase angle is changing in the same way. Phi minus 10, phi minus 1 is going from minus 10 to minus 90 degrees at several times with omega increasing. So with omega increases, the phase angle decreases also. Another example here, Shabab, we have find the steady state response of the following system. When we have the system is given by y dot plus 5y is equal to 4p dot plus 12p. For the input, p is equal to 20 sine 40. From this input, you will see that the magnitude of the input p, capital P, is equal to 20 Newton, and omega is equal to 4. So omega. So your response will have the same omega, or the output x steady state. For x steady state, it will have the same omega. Omega will be 4 radian per second. This is, we did it before, we see it. So now we know for the input, it's clear that omega is equal to 4 radian per second, and P is equal to 20 Newton. We have the input, Shabab, we have the output equation. We will look. You take y of s common from here and here. So we'll have s plus 5. When you take Laplace transform of both sides of the left-hand side, this will be equal to 4s plus 12 times p of s. So when we take Laplace transform of both sides, this is what we got. Now, if we take the ratio will give me g of s. It will be the output over the input. It's clear that the output is the left-hand side, because always the output will be in the left-hand side, and the input will be on the right-hand side. So it will be y of s over p of s. Y of s over p of s will give you 4s plus 12 divided by s plus 5. This is the ratio of the output over the input, which is y of s over p of s, and this is your transfer function that gives you the ratio of the output over the input. For s plus 12 over s plus 5, you can take 4 common in the numerator. You end up by having 4 times s plus 3 over s plus 5. Now you calculate the sinusoidal transfer function, just substitute s is equal to j omega. So it will be 4 here, 4. S will be j omega plus 3. Over s plus 5, it will be j omega plus 5. Now, Omega is known, we already found it, omega is equal to 4. We substitute by omega. So this one will be 4, J4, omega is equal to 4, plus 3 over J4 plus 5. Or you can write it real plus imaginary. You write it in this form. 4, 3 plus J4 over 5 plus J4. Now the amplitude of this, you take 4 square under the square root, it will be 4, because this one will be 4 square under the square root. 4 square under the square root, it will be simply 4. So it's 4 here. The magnitude of this numerator over the magnitude of the denominator is the square root of the real part plus the square root of the imaginary part over the square root of the real part plus the imaginary part. So you'll have 3 is 9 plus 16. 9 plus 16 is 25, square root of 25, over square root of 25 plus square root of 16, it will be 41. So if you have this one will be this, if you do this one with the calculator, you will get 3.123. The phase angle will be the phase angle of 4 plus the phase angle of 3 plus j omega minus the phase angle of 5 plus j omega. The phase angle of 4 is the real part, so its real imaginary part will be 0. So 10 minus 1, 0 over 4 will be 0. This is for the real part. Plus 10 minus 1, the imaginary part, omega over 3. This one will be here. And then minus, it's in the denominator, minus the imaginary part over the real part. It will be minus 10 minus 1, omega over 5. You substitute omega by 4, you will have 10 minus 1, 4 over 3, minus 10 minus 1 over 4, 4 over 5. You will find 0.253 radian. So now your output response will be the amplitude of the sinusoidal transfer function multiplied by the amplitude of the input, sine omega t plus 5. The amplitude of the transfer function, we found it 3.123. The amplitude of the input is 20. It's given here, it's 20. Times sine omega t is the same, plus 0.253, which is the phase we have found here. So at the end of the day, you multiply 3.123 times 20 will give you this. And then sine 40 plus 0.253. This will be your output, the steady state output. So the steady state output for this system will be by this, 62.46 sine 40 plus 0.253. Any question? Any question? Any question? So what we have seen so far is we did not include the damping, but now if we introduce damping, our equation of motion will be mx double dash plus bx dot plus kx is equal to p of t, where p of t is the input that is given by p sine omega t. So this is your input sinusoidal, p sine omega t. All we have to do is to find what will be jg omega, magnitude, Lp is known, and we need to find the phase angle, which is the phase made by jg omega. The annual expression will be the same. X will be capital X sine omega t plus phi. This will be your sinusoidal or the steady state response. Now, okay, if we take Laplace transform of both sides here, if we take Laplace transform of both sides, we will have ms squared plus bs plus k x of s will be p of s. And if you take Laplace here, the transfer function will be simply, if you go from here to here, the transfer function will be 1 over ms squared plus bs plus k. The sinusoidal transfer function, you substitute s is equal to j omega, substitute s is equal to j omega, by having this one will be k minus j, لأنه when you square s square it will be minus j omega square, j omega square, g square will be minus 1, so you will have k minus m omega square plus g b omega. K minus m omega square is the real part, j b omega is the imaginary part. Here we have to distinguish what will be the real part and what will be the imaginary part. The magnitude of this function, or jg omega, it will be the real part square. The real part square is simply this part, k minus m omega square. This is the real. And the imaginary part will be b omega, which is this one. B omega, which is this one, the imaginary part. So the phase angle will be the angle made by this one, which will be minus 10 minus 1, the imaginary part, B omega, over the real part, K minus M omega square. The 10 minus 1, this 10 minus 1 will be 0. So it will be 0 minus 10 minus 1. So that's why we did not write the 0, we wrote it like this. So once we know the magnitude and we have the phase angle, we can write our output response. That will be something like this. So this is the magnitude times the input. This is the magnitude. This is the magnitude of the input. So the total here will be capital X. And this will be your angle phi, minus phi. This will be phi. So if we observe this, Shabab, if we observe this one, that K over M is omega n square, if we observe this one, and B over K is simply twice zeta over omega n, we can simplify here by K, or we divide by K. If you divide this equation all over, you divide by K, by K, by K, by K, you will get the following. You will get P over K, you will get K over K minus M omega square over K plus B over K minus 10 minus 1 B over K. Divide everywhere by K. So P over K will be simply static deflection. You know, it's a force over K, a force over stiffness will give you the static deflection. K over K will be 1. M over K is omega n square. So K over M will be omega n square. So this one will be omega over omega n, the whole square. And B over K, we already wrote it in a B over K is twice zeta over omega n. So it will be twice zeta omega over omega n square. Sun minus 1, omega t, minus 10 minus 1, twice zeta B over K will be simply twice zeta over omega n. So here we can write also, omega over omega n, we can call it the frequency ratio, we can call it as R, and we write our equation X static deflection 1 minus R square plus twice zeta R square sine omega t minus 10 minus 1 twice zeta R over 1 minus R square. So this will be your amplitude of the output, and this will be the phase of the output, where here we are writing it in non-dimensional form. لأنه zeta is dimensionless and R is omega over omega, and the frequency ratio is also dimensionless. So we can further take this Y over X static deflection. So we will have the left-hand side is dimensionless and the right-hand side will be also dimensionless. So we take here, Shabab, if we take the amplitude ratio, this, we call it the amplitude ratio, Y over static deflection, we call it amplitude ratio. So the amplitude ratio will be 1 over 1 minus R square plus twice zeta R square. This will be the amplitude ratio. Y over delta static, we can call it capital X, or the amplitude ratio. And this one will be the phase ratio. If we look at them, this is how we wrote them. We wrote them like this. The amplitude ratio is X over delta static, 1 over 1 minus R squared plus 2 zeta R squared. And the phase shift will be simply twice zeta minus twice zeta R over 1 minus R squared. So the amplitude ratio here, Shabab, it is given to you to be in this form. when we have zeta is equal to 0, which means when there is no damping, and the amplitude ratio is equal to 1, يعني the amplitude ratio is equal to 1. معناته هنا this one will be 0 and this one will be 0. 1 over 0 will be infinity, and you have what we call the resonance. So when omega over omega n is equal to 1, we have the resonance, and you have to be carefully, and amplitude هنا goes to infinity. Resonance R is equal to 1, and zeta is equal to 0. You have to be careful. لأنه هنا you substitute zeta is equal to 0, you substitute R is equal to 1. This will give you 1 over 0. X over delta static will go to infinity. This will be resonance. You have to be careful for this one, which is this at this value here. Now, if you at these values, there is no problem if you start giving some values for the damping. If you start giving the values for the damping, this is what is giving you the amplitude. As you can see, with small damping, the amplitude is high. With the increased damping, the amplitude will be reduced. The amplitude ratio starts from here, and then it goes up to the maximum value, and then with increasing omega over omega n, with this will also decrease. So it starts smaller value, and then it increases to maximum, and then it goes to the minimum values also. So this is the values of the amplitude ratio, how it is increasing. This is, Shabab, you should know it. It's just the amplitude ratio. The phase angle will be also like this at certain, when zeta is equal to 0, when there is no damping, and omega over omega n is equal to 0, the phase will be from 0, and then at omega is equal to 1, it goes 1 like this, and then it goes to 180 degrees at pi. And then with the values of changing omega or changing zeta, these values will be varying from 0 to 3 pi over 4 or 3 pi over 2, and they will increase like this. These are the changing of the phase angle with the amplitude when we decrease, when we vary the amplitude ratio R at different damping ratio. We شباب هنا, if we have just one frequency, what we will see just this frequency. When omega over omega n, we see it like this. This is the omega over omega n, which is the frequency ratio, and this is 1, and this is the amplitude when it goes to 1 for zeta is equal to 0. We have seen this one last time in domain. In time domain, this was doing, it was increasing, the amplitude was increasing with time like this. Remember, Shabab? We will see this one, Shabab. I will just try to show it to you in a small video, because here we will have to do some vibration or in rotating mechanical system. Maybe we will start next lecture, maybe for the rotating imbalance, but I will just try to show it to you, Shabab. If you give me just 1 minute, I'll try to show it to you in the applications of having a sinusoidal input and sinusoidal output, their application, how they occurs. I'll show it to you. Just if you give me 1 minute, I'll try to show it to you how it works. I will say here, share application or share screen. I will share the screen with you. I hope it will work, screen 1 or screen 2. Shabab, did you see the washing machine? How is it doing? And the washing machine, when there is excessive vibration, it goes what we call imbalance. It is doing imbalance. And sometimes also you feel that you have rotating imbalance in your, I don't know if you see what I'm showing you or no.
I have it.
Do you see what I'm showing you, Shabab?
Yes, yes, we see it.
Did you see the washing machine vibrating under when we have
Yes.
explaining to you, if sometimes also you feel that you have in the مقود السيارة, when you are driving, you feel that you have the steering wheel is rotating, or it's causing imbalance. Why is this due? Or here in the washing machine also, why this one is doing this excessive vibration? Did you think about it, Shabab, why this is happening?
Yes.
Why is this happening, Shabab?
Maybe the distribution of mass is affecting the process.
So, Shabab, hina, this phenomena happens when we have, imbalance. When we have the, I'm not sure if this one will write. I will go back to my slides so that I can write on it, because I want to show you how we will do this. Yeah, I will go back to my notes. I'll just try to find. This is what we call its imbalance. Imbalance, we will start studying it, inshallah, بحول الله بكرة غدا بإذن الله. But I will just explain to you how this happens. How this happens. Hina, Shabab, why this happens? Because what we have here, when you have something rotating like this one, any equipment that is rotating, this is the center of mass. And this is this is the center of rotation, if you want. Center of rotation. And this is, if you want, the center of mass is somewhere here. This is center of mass. Center of mass. When, Shabab, the center of mass is not coinciding with the center of rotation, that this is what we call imbalance. The imbalance causes high vibration. And sometimes when you go with your car and you park it, or during the parking, or during when you hit a bumper, or when you high speed and you توقع في حفرة أي شيء, this will cause something, the imbalance to your car. So you will take it to the mechanician here, to the mechanics. He will fix it. He will do what, basically? He will do just, if there is mass lost from here, he will try to bring the center of rotation to the center of mass. He will bring them. So he will make the center of rotation exactly at the same center of mass, so that either by adding mass somewhere here or somewhere here, if the device will tell him where to put exactly the mass, where there is the imbalance. So he will put a small masses here. Maybe you noticed this in your cars. Did you notice it, Shabab?
Yes, we see
some weights, small weights in. And this is just to make it balance. You will balance your car. So there will be no excessive vibration. Similarly here, where the clothes in the washing machine, they go to one side, they are not distributed equally. The clothes will go like this here. They will get concentrated here. So the vibration, or the center of mass, will change, and you will see that there is excessive vibration. All you have to do is to go and distribute the clothes equally here, and you will restart your machine, you will see that it is working fine. I will stop here and then we will continue inshallah bukra. Let me just take the attendance today. So this will be our starting for our tomorrow inshallah bi'idhnillah bihawlillah. Shabab, it was the weekend, I could not post the solution, but I will do my best inshallah to post them either tonight or tomorrow morning. Let's see some solves problems for your exam. العلوة منير دغال بي فيصل
يس دكتور موجود.
اهلا وسهلا. مسعود يا عبد العزيز. الملاح ماجد.
يس موجود. يس.
كيفك يا شيخ ماجد؟
الله يسلمك بخير الحمد لله.
الحمد لله. القحطاني حسين موجود؟
موجود يا دكتور.
اهلا حسين. محمد يا عبد العزيز. اهلا عبد العزيز اهلين. القحطاني عبد الكريم. مشبب. الكريم. الشهري علي. رميح هاني. القرني علي. زهراني فارس.